Hello all, welcome to the webinar series of IEEE Joint MTT AP EMC and CAST Joint Chapter Islamabad. I'm Dr. Nushirwan Shoaib, the chair of the chapter, working as assistant professor at Research Institute for Microwave and Millimeter Wave Studies, also known as RIMS, at National University of Science and Technology, NUST, Islamabad, Pakistan. I welcome you all at this webinar series. We are basically located in Islamabad. Islamabad is the capital of Pakistan. It is one of the well-managed capital and one of the beautiful capital among the world. It has both natural beauty and business hub, and this is a place where we will conduct next year our first dedicated international conference on microwave antennas and circuits, also known as ICMAC 2021 in Pakistan. I hope all of you will join us in Pakistan, in Islamabad, for your talks and research webinars. So National University of Science and Technology Islamabad campus is shown here, and this is one of the campus of NUST. NUST has several other campuses in other cities as well, and in this campus the RIMS is situated, and it is situated here. So this Research Institute for Microwave and Millimeter Wave Studies is a specialized postgraduate institute that offers master's and PhD degree in electrical engineering with a particular focus on RF and microwave. Apart from just theoretical knowledge, we also have specialized safe state-of-the-art RF and microwave facilities, such as an anechoic chamber that works up to 40 gigahertz. It has both near field and far field measurement capability. We also have the electromagnetic compatibility interference lab that is basically used for teaching and also for pre-compliance testing as well. We also have microwave research lab and a PCB fabrication lab under the same roof. The idea is that the student, apart from learning their theoretical skill, can also design, develop, and test a system under one roof. This gives them a hands-on experience as well once they go to the industry. So today we are conducting the webinar number 17 under a webinar series that is basically started in view of pandemic COVID-19 in March 2020, and we are very pleased to host Professor Julian from University of Glasgow, UK, and the title of the talk is Radar Sensing in Assisted Living. A brief biography about the Professor Julian. He received his Bachelor of Engineering and Master of Engineering degrees in Electronic Engineering from Cork Institute of Technology, Ireland in 2004 and 2006 respectively. He received his PhD degree in Electronic Engineering from University of Pure and Marie Curie in France in 2011. He held a postdoctorate position with Guangxi Institute of Advanced Technology, Shenzhen, China from 2011 to 2012. He was a lecturer with the Department of Electrical and Electronic Engineering, the University of Nottingham, Ningbo, China from 2012 to 2016. He is currently the senior lecturer both in School of Engineering in Systems, Power, Energy Group within the Communication Sensing Imaging Lab at University of Glasgow, and in the School of Information and Communication at University of Electronic Science and Technology of China. He is also an adjunct associate professor in University Cergy-Pontoise in France. His research interests include radar system design, software-defined radio, and radar signal processing and health application. So we are very pleased to host him here at our webinar series. Without any further delay, I request Professor Julian to please proceed ahead and start his presentation. Over to you, Professor Julian. Thank you.
All right, so thank you very much for the introduction. And thank you for having me today. So let me share my screen then. Are you sure you want to share? Yes.
Yeah. Yeah. I just.
Can you see my screen now?
Yeah. You may proceed ahead.
Okay. Excellent. So. So I'm going to give you an overview of our activity in radar sensing in assisted living. This is a very niche area, and so this is a summary of the contributions of different universities. Obviously I'm not doing this all on my own. So the contributions are from University of Glasgow, University Cergy-Pontoise, Nanjing University of Science and Technology, and TU Delft. So well, let's proceed just now because you know who I am by now. So the context of this study. So globally, we have an aging population, especially in developed countries and also emerging countries. So if you take China, for example, you have, so let me change the pointer to a laser. So you have here the evolution of the population in China. You know, for 2050, you can see that it's heavily biased towards the elderly population. So there's a real need in terms of a change in paradigm in the infrastructure, because right now none of the countries have the infrastructure to actually welcome the wave of elderly people and the slew of problems that will come with it. So as we age, obviously, so people will want to have quality of life, and that becomes, you know, like an issue that comes at the foreground. There's an increased risk of fall. So when you're age 70 or over, you are very likely to fall at least once a year. There's between 33 to 42% chance of falling at least once per year. And as we are aging, obviously, we are very likely to carry chronic diseases. So the top one would be ischemic heart disease or stroke or chronic obstructive pulmonary disease. So there's actually an interest in self-tracking and monitoring at home your activity and seeing how you know, being observed outside the hospital can help maintain people at home longer. So those are actually directives from health institutions in China, France, UK, the US, and many other countries as well. So there's really a lot of work going on there. So there we go. So the concept of what we're trying to achieve, and currently this might look quite simple, but is to have actually radar units set in an apartment, you know, collect the signals, process them, and then classify the information. And the very first mission we have is to detect activities of daily living. So those 6 activities, bathing, eating, toileting, transferring, dressing, and walking, are the bare minimum activities you're supposed to be able to do on your own to be considered able to survive at home. And yes, I did not say live, I did say survive, because there are then extended activities of daily living that shows that you can live independently at home. But just doing those 6 already is challenging, and I'll explain why in a minute. Another dimension of this is to look at vital signs, and this will be in the emphasis of what some of our colleagues do in Nanjing. So I'll present that a bit later. Because if you combine the two here, activities of daily living and vital signs, you can then infer a lot of information about healthcare. So for example, you can look at respiratory disorders, sleep stage monitoring, and a lot of other information about a patient's health. And a lot of the hospitals, so pulmonary department, geriatric departments, are very interested with these technologies. So we're currently working with them to actually improve what we can do for them in the home environment outside of the hospital, or, you know, also known as primary care units. So obviously radar is not the only technology available for assisted living, but let's have a quick tour of what we have available. So we have cameras, or, you know, it could be infrared, depth camera, or just standard visual cameras. They're actually quite good in terms of detecting activities. Vision-based classifying algorithms are actually working very well. They do have problems in terms of lighting. If you have kind of a sun glare, you know, in the field, or if there's low luminosity. then the performance may decrease. But this is not exactly the main problem of those sensors. The main problem is actually privacy. So let me ask you this: how many of you would be willing to have a camera installed in the toilets or in the bathroom to monitor their activities? I think almost 100% of people, if not 100, would say no way. Maybe in the living room, in the kitchen, and even then that would feel quite intrusive. Wearables have actually been studied for human activity recognition for some time, and they have very good accuracy. So the best position for wearables, the actual best position is actually on the waist. The second best would be actually on the wrist on either side. But the problem with those, especially with cognitively impaired patients, because you're talking about the elderly population, is for them to remember to actually wear them. And if you wake up at night to go to the bathroom, and that's where accidents happen as well, you need to remember to actually put it on for it to be effective. And they might need to be recharged as well. So, that would involve changing the routine of the patients. So that could be a problem in terms of acceptance of the technology. You then have ambient sensing. For example, you have acoustics, microphones. But then again, there's a small problem regarding privacy issues and a sense of an invasion of privacy. Then you have passive infrared sensors, the sensors you use for lighting a room when someone is in it, and then switching it off if there's no activity inside. So those are actually quite well accepted, but the level of information you get from them is rather coarse. So it's good to know if someone is in the room, and you can build an activity map of where the person was in the house during the day, but you're not able to say what they were doing. So inferring finer grained information is actually more difficult. Another option is smart floors with capacitive sensors, and you see it here, for example. So those are actually quite good in terms of collecting data and everything, but that requires refitting your entire apartment or living area with those, and they're rather costly. And we had a running with an insurance company once, and we were pitching this technology for them, and we asked them how much they would be ready to pay for a system if they could prevent falls and collect information on the well-being of the insured people. And I said, well, a system, the whole system, including sensors and computers and communication, with the outside, 500 euros tops. Anything more than this, forget about it. So smart floors are sort of outside the question. So here we're coming with a very interesting problem where you have the richness of information a sensor can actually give you against the perceived privacy people have. So we're seeing here with visible video, we get a lot of information, but people don't like having those around. And we find here the PIR sensor was, in terms of richness of information is pretty low, but then people feel quite safe with that. But with radar, well, quite a lot of you would have Wi-Fi at home, and elderly people would have those as well. For the most part, not everyone, but most people. So it's more likely to be accepted as a useful technology. So you get very rich information from those sensors, and at the same time, you don't get any, visible optical kind of data from the scene, so people would be more comfortable with this. So there's a lot of interest from industry in terms of using such technologies to try and detect activities within a home. So coming back on why radar, so it has a multitude of benefits compared to existing technologies, so you don't have to rely on the user acceptance or compliance, because you can just affix a radar on the wall and then they go about their daily life and they don't have to do anything special. It's just there and does the job. They don't need to carry the device. There's no visual record or identifiable data about them. In case of a security breach, there's no obvious signs of what's in the house or who is in there, unless you know exactly how to use the signal processing and the parameters of the system, which is quite unlikely. And there's no need to remodel the environment to install sensors. And on top of that, even if it's affixed on the wall, you can put that behind a radome that you could personalize. So that would sort of remove the stigma as well of having such a system installed in your home. So it's very important from a user acceptance standpoint. So now that I've explained why this is interesting as a technology, we can look at what people have done in this for the most part. So typically speaking, so we would actually collect data, like with measurements or with simulation environment, but we have a tendency to do more experiments ourselves, and we would use the micro Doppler signature, which is actually a representation of the evolution of speed as a function of time. So radar, in radar, the primary information that's collected is range, and from the variation of range over time, then we derive the speed. So in the micro Doppler signature here, we've actually suppressed the range information, and we only keep the Doppler information. And sorry, and as you can see here, the center of, so here you have the center of mass of the target. So this is actually a person walking. So the center of mass would be your trunk, when you're moving towards the radar. And the fluctuations around the center of mass here would actually be the relative speed of your limbs as you walk, and your arms and legs are swinging back and forth as you're walking. So you can extract information about the strengths of the signature, is a reflection of the radar cross section. The width of the signature corresponds to the bandwidth of the Doppler signature, and you can identify peaks and a lot of different parameters that you can extract from these. So we need to extract features from micro Doppler. Here you can define them yourself empirically. They could also be physical, like the center of mass or something. You could also extract them automatically with singular value decomposition, for example, or others. And then you'd come and take those features and try to apply a classification algorithm like KNN, support vector machine, discriminant analysis, or neural networks to try and separate the different clusters from one another to try and define which activity has been performed in front of the radar. So this is what 95%, maybe probably more, of the publications in this area are actually using as a way of classifying data. So most of them use micro Doppler, and the way feature extraction classification is done from this varies quite a bit, but it has limitations. So those are spectrograms, also known as micro Doppler signatures. And you will see very good performances in the literature in terms of separating activities using spectrograms. But what they fail to mention most of the time is that they use activities that can be distinguished quite easily visually by just looking at the signatures. So the job of the classifying algorithm is actually quite easy. Now, if you take signatures that are meant, that are actually designed specifically so that they actually look similar in terms of speed when you look at them. So here you have bending and picking up a pen or tying a shoelace. They're quite different. Well, sorry, they're quite similar. And if you look at tying a shoelace in a frontal fold, they also look quite similar, but yet they're very different actions. Now, if you could access different radar data domains, so I mentioned that the primary information you get from a radar is range. So range could easily distinguish between tying a shoelace or a frontal fold. If you look at the spread in range, if you have a sufficiently high distance resolution for your radar, and so with the advent of radar in automotive, so the radar units have become much cheaper. The bandwidths have improved quite a bit, so now we can easily get 20 centimeter resolution or less for a radar, which is actually good enough to distinguish limbs from the main body. So we get very accurate information, and that means we can exploit the range information we get as well. So what I just showed you is actually the spectrogram. It's over here. But what we get now with the new radar systems is much richer in terms of data representation domain, and that opens up a lot of possibilities in terms of what we can do. So we can actually classify directly from the raw data, but that requires, very complex classification algorithm, in terms of size and hyperparameters. But you can actually use any of the data representation domains here to try and extract features to distinguish actions from one another. So range time, so looking at how the range evolves as a function of time is one of those data representation domain. And you can obtain this from the raw data using range compression. So most radars would do that with matched filters, or if we're talking about an FMCW radar using stretched processing, you would simply do an FFT on the raw data to obtain the range time, because the analog signal has been stretched so that the frequency you digitize is actually directly proportional to range. So you have two different possibilities there, but the representation domain is the same. Now, if you take a small window here and perform an FFT, for example, on each of the range bins, then you obtain a range Doppler representation for one instant in time. And then if you move that window along, then you can obtain different images there as a function of time. So to obtain a spectrogram, what we do is actually we suppress the range information and have and sum all the Doppler together in one vector, and that's one slice of the spectrogram here. And if we repeat that for every image, then that's how we actually build the spectrogram over time. Now, you may have noticed that in your spectrogram, you may have periodic signals. So if you perform an FFT again on each Doppler bin, then you can obtain a cadence frequency representation that shows periodic signals over here. So this is for walking. So this can be quite useful to separate periodic activities. You also have spectrograms here that look at the power in the received signal over here, and those are actually quite recent, and they're actually derived from range Doppler representations, where you come and extract surfaces using a threshold to extract a 3D range Doppler time representation, or you could have simply an integration over time of those images. And this one here, the radar data cube, is actually just a variant of that second one here. And so that gives you a lot more degrees of freedom in terms of what you can choose from to extract useful salient features from those to try and classify the data. So here, you have the most variety, because this is actually these three have been around for quite some time. So they've used CNNs, stacked autoencoders, convolutional autoencoders, LSTM, and SGRU units like this. So those two are recurrent neural networks. For range Doppler, so that you can actually use CNN to extract automatically features directly from the image here, and then use a superimposed LSTM to collect the information from the CNN, then try to link the information temporally between the different frames here. So over here for range time, you can use recurrent neural networks, because unlike vision-based algorithm, the images you see here actually have physical meaning. There's time information being displayed here, so we might be able to actually use temporal links in here, so going forward and backwards. So you have bi-LSTM, so bidirectional LSTM as well. So there's a lot of different possibilities there to try and get information from here. And in terms of the new representations, so because this is a 3D surface, so a 3D CNN can be designed here. So this is based on a PointNet algorithm. So we've just published something in the IET Radar 2020 conference on that particular algorithm here. And here, this is from one of our competitors using multilinear PCA extraction of features from a 3D surface here. So just to say that I'm not bringing any answers here, I know, and we're actually working on new radar data domains representation as well. So our competitors are working on the radon transform, radon, not random. No, it doesn't know that word. Fair enough. Which is used in circular SAR image reconstruction, or like medical imaging, and we are working on deriving cyclostationarity features. This is used in telecommunications to recognize signals based on their periodicity, to see if that can help for human activity recognition. So lots and lots of different things, and different contributions to be had here and this is, you know, booming at the moment. So very interesting things to be doing. And we also have a public database that you can use to try your hand at it if you're interested. I can talk about this a bit more later. So now we're going to move to what our colleagues in Nanjing are doing. And this is also very exciting. So this is on vital signs monitoring. And so over here, you're looking at recognizing breathing and also heart rate monitoring. So recognizing breathing with a radar has been around for 40 years at least. So I mean, this is not very exciting. Now, heart rate monitoring is a bit more complex now, because you have here an example of what vital signs, like from looking at it spectrally looks like. So here is the harmonic for breathing, and then you have the harmonics over here for breathing, and you can see over there that you have your heart frequency, and they're actually quite close. So you actually need to use sophisticated signal processing. So an FFT will just, you wouldn't be able to tell which one is which. Music, you're getting closer, but it's not quite clear which one it is. But using atomic norm minimization, you're getting closer. And if you use then stepped atomic norm minimization, then you're even closer. But that requires a priori information on the range of where the heart rate is going to be located. And it's usually close to the third harmonic there. So that's how they're able to do this. And they're getting very close results compared to the ground truth. So I hope you can see the respiration belts that the students are wearing over here, and how the radar is able to closely track those, especially if you have two different people in there. And this is using a decomposition method, because you are actually getting both those signals at the same time. And you can do that with up to 8 people, even if they are at the same range, at the moment. So this is actually quite impressive. The only downside for this particular method is that the people have to be static for the radar to be able to extract that at the moment. Static, not ecstatic. Okay, so in terms of applications of those, so this has been deployed in a hospital in Nanjing, and so they've actually monitored patients for several days, and with the help of doctors, they've actually labeled the raw data they were getting from the patients being monitored 24/7. And to their surprise, they were actually able to identify breathing disorders actually vary depending on the time of day. So the patients were not always displaying their primary breathing disorder, but they were displaying different ones. And I think they reached over 87% accuracy overall in distinguishing the breathing disorder with this. And this is actually the results they had in the early days. So this has gone and evolved quite a bit since then. But the biggest application they have at the moment is on sleep realm monitoring. So to distinguish deep sleep, light sleep, REM cycle, and wake. So if you're going to a sleeping lab to monitor how you're doing in your sleep, this is the equipment you have to, to actually monitor your sleep patterns. That's not exactly comfortable. So the readings you get are actually quite biased, but you could actually have a radar overhead looking at your vital signs, how much you move in your sleep and everything, and derive those informations. So they also got something like 85 to 87% accuracy on their early stage developments. But since then, our colleagues have measured thousands of patients for several days, and they're in the process of actually getting all of this processed and everything. And I've been promised some exciting results soon, so I'm actually very excited about learning more about what they're doing, because they're actually doing very, very well in that area. So now we're moving more into the challenges of human activity recognitions and also vital sign monitoring. So it's in terms of the AI topology. So most of what we look at the moment only has one sensor, most likely, but we will have inside a home a multitude of sensors, and they might be also different in terms of the sensing modality. So I talked about different sensors, wearables, ambient sensing and everything. And I said why radar was the preferred modality, but it doesn't mean that we can't capitalize on the others to try and improve performance. So there comes a first design challenge for the AI topology, that we may have sensors that work at different speeds. So how do we actually, include them together within the same, AI structure? So where do we fuse the information? Do we do it at the signal level? If we have similar sensors, do we actually fuse the information at the feature level or at this decision level? And if it's at the decision level, do we implement a hard fusion technique or a soft fusion technique? So this is, the first kind of a design problem. Another is, how do you actually work on reducing the number of hyperparameters you have to tune? So here I give an example of a paper. This is actually from Gang Lee's paper on human activity recognition from 2018. It was actually very interesting. So using a multi-static radar. So since the first steps are actually quite similar in terms of extracting information from spectrograms, the first 3 layers were actually trained similarly for the 3 nodes, because the start of the job is quite similar, but they look at the target from different angles. So then the force convolution layer is left to actually learn things on its own, and then you flatten the whole structure. You use max pooling to reduce the size of that vector, and then do your classification. And that was actually quite successful. And it was quite successful in terms of the classification accuracy, but even more interestingly, the robustness in terms of the size of the training. Because one of the biggest problems in radar, so unlike vision, we do not have databases with billions and gazillions of images, in banks sitting there. So the radar database I was telling you about that we have put online with thousands of signatures in there is actually one of the biggest available out there in terms of human activity recognition. So we have to deal with training AI algorithms from very little data. So we need to be able to create algorithms that can generalize from using a small amount of data. So here you can see how it's robust, on the different chaining. It's still, obtaining very good information. Another thing as well, so since you would have a distributed sensor network, a very important question if you think about implementing it, pragmatically. So where in the processing chain for your AI topology do you actually transmit the data to a central node for processing? So where do you put the intelligence? Do you put the intelligence closer to the sensor to do more processing and then transmit fewer data? Or do you put no intelligence in there and just transmit everything raw? Or do you put this somewhere in the middle? And this is another optimization parameter there for your AI topology. So there's a lot there as well to be done. And since we're talking about implementation, so we can look at the challenges for real-time processing. So obviously, parallel architectures, are going to be important, but they need to be low footprints as well. So we'll need to do the data acquisition, processing, and feature extraction, but with low footprints in terms of cost, energy consumption, and also how much silicon it uses. So currently, deep learning implementation is mostly done using GPUs. They're quite good, fast prototyping. They process very fast, but they have a big energy footprint. Whereas FPGAs could actually be a nice trade-off in terms of the speed you get for the amount of power you consume. So they're more energy efficient. They can use massively parallel computing at multiple data rates, and that's very interesting if you use different sensing modalities. And you have rapid prototyping now with all the IPs that you get from Xilinx or Altera. That's now Intel, I think. This year Xilinx actually released a deep neural network library engine for their Alveo boards. So they're actually releasing IPs to implement deep neural network architectures on embedded platforms. So that helps you, prototype faster as well. So FPGAs are becoming more and more interesting for a pragmatic implementation of these algorithms as well. Another interesting thing is RF SOCs as well. So it's the radio frequency front end, fully built in one chip, and those are actually software defined. So yeah, you can actually reduce the amount of energy consumed by your RF board. For example, if you sense that nothing is going on, you can actually turn, the performance down to just a presence detector, for example, and start defining strategies to save energy when no one's home, because this will be reflected in the energy bill at the end. And what we envisage being the problem, and that sort of falls back to the problem I was discussing for the AI topology, and where do we actually split the information? Where do we put the intelligence in? Because the network on chip will be the bottleneck, is how much information can you push through the central node to actually do the processing. So this will likely be, kind of the hard point in the future. And another one that we often forget as well is the precision. So what happens to our algorithms when we have fixed precision or even half precision floating point? Because even using signal processing and the classification algorithm, as soon as we start reducing the precision, we are losing in terms of accuracy. So it's not unheard of to lose 20 to 30% accuracy when moving to fixed precision or half precision floating point. So we'll need to define, new AI topologies as well, and signal processing to make sure we can maintain precision even on embedded platforms. So that's sort of problems, for the future. And as I mentioned earlier as well, so we have to work on the fusion of different sensing modalities. So there's a lot of work to be done here. And in terms of lessons learned, so usually fusion helps in terms of how much accuracy you get when you use different sensors together. Now, I say usually because we've had some mishaps in that as well, where we defined algorithms which actually decreased the accuracy, which were not so good. But mostly you actually get, so here you see for 2 different radars, increased accuracy quite significantly as well. But as you fuse the data, you get more and more features, and more features doesn't necessarily mean better accuracy. So you can see here that you reach the peak over here with only 15 features, whereas we actually have 38 features. So looking at the saliency of the features you're using will help as well to optimize the performance of your application. And not just that, but we've actually looked at the target population for our algorithms. So what we do in labs and everything is very good. It helps advance the research as well, but you should not lose sight of what you're doing. So you're designing algorithms, so in our case for assisted living, so the patients we'll be dealing with are old, and you do not walk or perform activities in the same way whether you're 20 or 98 years old. So there is a need as well to customize algorithms for the target population as well. And if in the database we have online, so our volunteers for the measurements, they range from 23 years old to 98 years old. So you can actually see the differences in their signatures, which is very, very different, and makes the job very hard for a classifier to actually distinguish between the two. So you have to remember this. And another one of the challenges that's forgotten is aspect angle, and this is where in most radar applications people actually just perform activities in the line of sight of the radar, and people don't always move in that direction. They they'll be coming sideways or at an angle or something, and your algorithms still have to recognize activities reliably. So this is the signature for a jumping action for a monostatic radar, and you can see that at 45 degrees it's still more or less the same, but at 90 degrees it looks completely different. So if you change a network on something like this, it will not recognize this as jumping. So you need to design sensors, your radar, so you can actually deal with this. So we tested different radar geometries in simulation for now, but I'm currently working on validating in this with measurements. So I have one radar at home now that I need to install it and start working with it. And so you have the multi-static one where you have one transmitter and several receivers, and you also have an interferometric one where the transmitter and the 2 receivers are actually equidistant there. And the interferometric channel looks at the difference between the 2 receivers and integrates that over time. And for the same action I've shown you for jumping, you can see that when you're in the line of sight of the radar, the signature is very small, but when you're coming sideways, it's actually improving greatly here. So by combining those two, we've been able to maintain 97% accuracy from 0 to 90 degrees overall for the different actions recognized, whereas monostatic kind of breaks down pretty quickly after 35 degrees, whereas multistatic can maintain longer, up to 40, 45 degrees, but then decreases as well. So that's very important to keep that in mind, and keep developing architectures that are robust, for pragmatic implementations. And the next frontier is actually working on continuous data streams, because a lot of the work look at discrete activities. I'm measuring jump, and then that's it. I'm measuring walking, and then that's it. And if you put them back to back, and people actually perform those activities in a stream, you do not have those pauses or those discrete elements, that are easily separate. You can easily segment that to try and identify the data. So we're now working on continuous data streams with bidirectional LSTM and various fusion techniques to try and classify things on the fly. We're getting 90+ accuracy, 90+% accuracy there, but there's still kind of a lot to do in there to try and improve the accuracy. So this is sort of where we are at. I hope you enjoyed the talk, and maybe you can ask questions. And thank you for listening. I hope I wasn't too boring.
Thank you very much, Professor Julian, for a very interesting talk. We have few questions, so I can ask the question one by one.
Okay.
Okay. So the first question is, what are the impacts of wearable sensors on human health? And also comment on what are the tests performed on wearable sensor for compliance, like SNR test for mobile phones.
Okay, so the first question is the effect of wearables on the health of patients, you say?
Yes, that's true. Yeah.
So wearables, don't actually have much impact, because they need to transmit data somewhat, but the wireless signal that comes out of it, the amount of data is quite small, and I wouldn't think there is actually much impact there. The biggest problem there is with this is what I mentioned earlier, is actually getting elderly patients to try and use them. And from experience, by talking with nurses that actually work in people's homes, they actually go to different elderly people during the day, and also a company that works with providing such services with wearables for elderly patients, for alarm systems and their well-being. They all say the same thing. They are not always very reliable, especially the ones that are commercialized, and a lot of the elderly patients are actually reluctant to use them. So because of the stigma associated with it. So, but I don't think there is actually a health problem, related to this. Now, your second question was about what again, please?
Sorry. So the next question was about the SNR test. What are the compliance tests for these wearable sensors? For them, if you would like to commercialize them, so are there any compliance tests that are available for these sensors?
So for the compliance tests, obviously we need to meet the norms of the country in question. If it's emitting any signals, it would need to actually be compliant with the emission regulation units, limits for patients' exposures to radio waves. So I think there's actually a certain rating per kilogram. So I think 4 watts per kilogram is actually very harmful. It's kind of the upper limit, you know, and it's quite bad. 0.8 is for occupational use. So when you're aware that there's actually emissions, and I think it's 0.04, if I'm not mistaken, or something like that.
Yeah, there's some standard limit. Yeah.
Yes.
That's watt per kg that is allowed. Yeah.
Yeah. So yeah. You know, you'd have to comply to this if you want to commercialize something.
Correct. The next question is regarding the radar architecture. So someone has mentioned that there's a huge amount of DC offset when we talk about continuous wave radar homodyne architecture. So how we compensate that DC offset?
So there's actually quite a few techniques to compensate for DC offset. Let me pull a document for this, if you allow me just 1 second.
Sure.
So that would be research. This is not going to be a presentation, it's going to be a document, because I did a study for this at the beginning of the year.
No problem.
So Teams, share, and that one. There we go. Can you see my PDF document?
Yes, we can see it.
Right, so just have to go down quite a bit, and we're going to get there. Here we go. So super resolution. So yes, so this is referring to CW radar and also FMCW, you know, and it's linked with the arctangent. It's mostly for vital signs, but so to avoid problems, you have differentiate and cross multiply, which is one technique to actually circumvent this a little bit. The other one, well, you have an extended DACM, which is just trying to make sure that you can even better compensate for the DC offset. You can also use a 6-port interferometer to try and do this as well. So the only problems with those techniques is like it sort of multiplies the amount of hardware you need from the get-go to compensate for DC. But you know, this works quite well, and if you don't have too much bandwidth, then this is actually not that expensive. So you have, well, you know, this is quite similar. This is just using a different technologies. This is self and mutual injection locking. So this allows to actually kind of increase exponentially the frequency differences you get from vital signs to try and improve the SNR quite drastically compared to classic methods. So that's actually quite interesting as well, and this is evolving. So this is actually mostly done in Taiwan because this is a proprietary technology here. It's Professor Horng, H-O-R-N-G. You have complex signal demodulation, and you can have state space methods. So those actually work quite well, but they're actually quite complex. So that's actually increases sort of your loading in terms of signal processing. So you actually have quite a few ways to go about it. There's quite a bit in the literature on this, and there's also, you know, trying to manually, well, kind of tweak your front end to try and reduce DC, but you know that requires calibration at the beginning as well. So there are different ways to go about it, but this is not a simple matter, because all of those techniques sort of require specific changes in your RF front end and signal processing, so they need to be done. You know, it needs to be co-designed. So you need to have experience both in the hardware design and the software design, signal processing, to compensate for that. If that makes any sense.
Yes, I think you have shown a number of methods and techniques to carry out the current task. So I think we are short of time, so I take one or two questions. The one question is, would, if we move from to millimeter wave frequency radar like 60 or 77 gigahertz, so will help in improving the real-time vital sign monitoring?
Will it improve what, sorry?
Real-time vital signs monitoring.
So with millimeter waves, so it will actually improve, you know, in terms of the fine changes, especially for the heart, because the wavelengths is much shorter and is becoming, you know, is starting to get in the same range as the variations you get from the heart motions, because what you have is the heart just beating behind your rib cage, and it's making it move by just a couple of millimeters. So and you can see that variation, you know, throughout, you know, like, well, all around. And surprisingly enough, the best way to see it is from behind. So you get the biggest variation from the heartbeat if you look at it from the back, which when I first learned it was actually quite surprising. So I would think that using millimeter waves would improve in vital signs. The problem you would get, you know, in terms of this particular application with millimeter wave is the fact that the Doppler signatures will actually increase quite a bit. So that will require much more frequent pulses to try and avoid problems with sampling the Doppler activity, so that you don't actually violate Shannon-Nyquist in observing the events. But yeah, definitely think there's a good possibility there, and we've actually purchased a couple of radar units at that range, and well, when the buildings will reopen, I might be able to actually check my parcels to try and play with it.
Yeah, sure, definitely. I hope the situation will become better very soon. Maybe this is the last question. Regarding different software packages that you have used to simulate all these radar and the data.
So different software packages?
Yeah, for example, which kind of software you have used? Yeah,
I'm using MATLAB, and I'm actually writing the simulation software myself.
Oh,
but there is actually one that has been released recently. If you want to check it out, let me check the name. Passive radar. So preprint. So it's actually from UCL, I think. It's Simul. I saw it recently. Let me try and Google it. The name is, it's Simul something. Chrome. There we go. because I have a friend of mine that sent me this. So signal radar. It's actually quite recent. I think it was last month it was released.
Okay.
So it's I'll find it.
you took this as a challenge. Yeah.
Simhumulator. So SIMHUMALATOR. Yes, so
Okay.
that's one. That's the one. I think. Yeah, I knew it had a weird name with Simhumulator in it. So yes.
Yeah, maybe it's a combination of multiple words. Yeah.
Yes. So so that was actually just released last month, and this is actually using a graphical user interface, so you can configure your radar and you get some emulated radar signatures. So I do something similar. It's just you know, they have put a GUI on it, and I don't have one. I just do my own thing.
Yeah, I think writing software packages by own is a very tough job and time consuming as well.
True.
So I think, yeah, it will be good to use the already developed software, especially with some good graphical user interface, so that we can spend more time on analysis as compared to writing the software.
So if you want to get started on writing simulation software, so you can just get you know, the Victor Chen book on micro Doppler effects in radar, and you get, you know, like a MATLAB code with it of a working simulator just for one action, but then you can actually incorporate your own actions, and this one is cheating a little bit in terms of how you simulate the radar echo, but that saves in computer efficiency. So there's a trade-off in terms of how accurate you want to be and how much computer power you have available. So, but this could be a good starting point, at least.
Yes, you're right. So yeah, I also encourage the researchers to contribute in different fields as well, especially from programming point of view, so that it improves your thinking and how you can proceed ahead. So I think that's it from the question side. I think we also have used a lot of time, I think more than 1 hour. And thank you very much. So I conclude this webinar with thanks to Professor Julian for your time and this very informative talk. And I also would like to thank all the audience who were with us and attended this talk. Hope to see you at some other occasion, Professor Julian, maybe next time, next year in Pakistan, because we also conducting the first dedicated RF and microwave conference in Pakistan. So I hope I will see you in Pakistan next year as well.
Well, we'll see how the pandemic evolves, and fingers crossed.
Yeah, yeah, fingers crossed. Let's hope for the best, and let's see how the things goes on. Okay, see you sometime later. Have a nice day, and thank you very much for the talk. Bye-bye.
Likewise. Thanks. Bye now.
Bye.